Okay. Let's start talking through this conditional probability stuff. So going back to probability stuff we were working on earlier in the chapter. So there for our definition, it says the conditional probability of an event B given an event A, and then they write it as probability B, and then they put that little line there, and then the A, and it's always the intersection of those two groups divided by the probability of whatever the last letter is. So if the last letter is A there, it's divided by the probability of A. So basically these are like more dependent ones where like they depend on each other, like so something's already happened and then what's like happening after that. So it says the chance that some outcome B occurs given another event A has already occurred. So something has already happened, and then what are the chances from that the B is going to also occur? Okay, and we'll do some examples kind of mapping that out. And then, like I said, that tree diagram there, not a bad one to have because they're gonna ask you to do some tree diagram stuff. What this is supposed to represent is like a medical type situation where like they're testing a patient to see if they have some sort of disease or sickness or whatever. The top branch of that is the patient actually has whatever the sickness is. The bottom branch of that is that they don't have it. Now, when the results come back, you could actually get, either a positive result or a negative result, but those results aren't always 100% accurate just because it's hard for anything to be 100% accurate all the time. Obviously, with medical stuff, they try to be as accurate as possible, but it might not always be. So what it branches off here to then is, so the patient actually is sick or has the thing, more than likely they're probably going to test positive for whatever that sickness is. But sometimes what will happen is they'll actually test negative and they'll actually have the sickness, but they'll test negative. That's called a false negative, okay, where they are actually sick, but the results say, hey, you're not actually sick, okay? So sometimes that'll happen. The opposite of that then would be the patient doesn't have the condition, but then when they do the test, if they test negative, then that's accurate, that's what it's supposed to test. But occasionally they might actually test positive. That would be called a false positive, where you don't have the sickness, but they actually tell you you do have the sickness. That's why sometimes they'll run the test multiple times, or you'll go to like another doctor for a second opinion or that kind of thing, because they try to be 100% accurate, but just like anything in life, you can't always be 100% on stuff. Okay, so let's hammer out some of these examples then. So first example here, I'm going to do this one as a tree diagram one. So it says, let B be a person eats a good breakfast. L is a person that eats a good lunch. And then it says, suppose a group of 80 people, or the group is 80 people, 43 eat a good breakfast and a good lunch, 21 eat a good breakfast but not a good lunch, 12 eat a good lunch but not a good breakfast, and then the rest eat just junk all day. They don't eat a good breakfast or a good lunch. Okay, so like I said, I'm going to try to set this up as a little tree diagram here. So my first couple branches, I'm going to have a branch for people that ate a good breakfast, and then the opposite of that, or like the complement of people that didn't eat a good breakfast, would be people that did not eat a good breakfast. So I'm just going to go B for breakfast, and then not B for people who didn't eat a good breakfast, because those are the only two options. You either did or you didn't. Okay? Now off of that, I'm going to do the lunch ones. So if you ate a good breakfast, and you also ate a good lunch, you would be in that one. Okay, and I'm just going to do L for lunch. Okay, so that was good lunch. Now, again, if you didn't eat a good lunch, the opposite of that would be not eating a good lunch. So that would be not L. So you could also eat a decent breakfast, not eat good at lunch. And then you would just do the same branches off the not breakfast one, or not a good breakfast. So if you didn't eat a good breakfast, but you did eat a good lunch, that would be that one. And then the other one would be not a good breakfast and not a good lunch, which is probably the category I fall in. Don't give me that look. I don't have time for breakfast or lunch. I got work to do. Okay, so then we got to start filling in like our probabilities that kind of match with this. So like that first one, so we got a total of 80 people. 43 eat a good breakfast and a good lunch. So the people that are good breakfast and good lunch would be in this category here. We've got a total of 80 people, and 43 of those people ate a good breakfast and lunch. Zoom that in so you can see a little better. So that would be 43 out of 80. Next one it says there is 21 ate a good breakfast but not a good lunch. So good breakfast, not a good lunch would be 21 out of those 80 people. Next one is 12 eat a good lunch but not a good breakfast. So they're in the good lunch group but not in the good breakfast group. So that would be 12 out of 80. And then the last group, they say the rest eat neither a good lunch nor a good breakfast. So what I would do to find however many's left, I'd just do 80 minus those 3 that we already had. So like minus 43, 21, and 12 together. And I think that's 4 is what I've got on my sheet. So if you just subtract all your groups there from that total of 80, there should be 4 people left. So that last group that didn't eat good either meal would be 4. So then once you kind of get a visual of what that's going to look like, then you kind of start filling in the things here for the probabilities. So the first one, we want the intersection of the people that ate a good breakfast and ate a good lunch. So if we're looking for where those are the same, so good breakfast people are up here, good lunch group and good breakfast group would just be these people, right? So that would just be the 43 out of 80 because it's breakfast and lunch, and where they cross would be that group. So that first one's just 43 out of 80. If you want to take it to like a percentage, you could do that as well. Just do 43 divided by 80, which is like 0.5375. So like, let's just go like approximately 54%, something like that. I don't know which way they really want it. I don't care. It doesn't say one or the other. And then B, they want us to find one of those conditional ones where it's the L and then the line B. So when we figure out these ones, it's going to be the probability of the intersection of those groups. So the probability of the B and the L crossing each other divided by the probability of whatever the last letter is. So the last letter there is B, so divided by the probability of B. So conveniently with this one, we just found the probability of the intersection, right? Because that was our answer to part A. So we already know the probability of the intersection of those groups is going to be that 43 out of 80. I'm just going to put that on top. My bottom then is the probability that I ate a good breakfast. Now here there's 2 groups of people that could be in the good breakfast category, right? Because we have, so breakfast would be these 2 branches. All of these people ate a good breakfast, as well as all of these people ate a good breakfast. So you got to combine those 2 together to get all of the people that ate a good breakfast. So you're going to combine the 43 out of 80 with the 21 out of 80. And then there, since they're all out of 80, basically the bottoms can just all kind of cancel out there, and it's the same as like 43 out of 43 plus 21 would be 64. So 43 out of 64. And then again there, you can either leave it like that, or you can figure out what it's approximately equal to by dividing that. So 43 divided by 64 is about like 67%, somewhere in that range. And then C is asking us to go the other way. So now they want us to find the probability of that B and then the line L. So probability this time, B line L. So the top is still the same because it's the intersection of the 2. So probability of B intersection L over, and then this time our bottom probability is just the L group because that's the last thing there. So probability of L. So again, our top is still going to be the same for the intersection, 43 out of 80. But our bottom is our 2 lunch categories. So our lunch categories are going to be the ones that's the 43 out of 80 and then the 12 out of 80 as our 2 with the capital L's there. So I'm going to add 43 out of 80 plus the other lunch one for not a good breakfast was 12 out of 80. And then same thing, since all of those are out of 80s, the 80s can just kind of cancel there. So it would be 43 out of, and then 43 plus 12 would be 55. And then again, you can just figure out what that's approximately equal to. So 43 divided by 55 is like 78-ish. So 78% of people would fit in that category. Okay, so that's using the tree diagram. So that's one way to do it. And I think on the assignment, a lot of times they'll tell you which method to go, like draw a tree diagram or whatever. The next one, I'm going to do it as a table. I think that these are actually the contingency table things that we were actually working on with yesterday's stuff. We just kind of have to set it up by ourselves here. So it says, suppose 1 in 500 airplane passengers carry some hazardous material with them onto a plane. Further, suppose that an airport screening device accurately identifies 98% of people with the hazardous material to pass through, and then accurately identifies 99% of people without hazardous material. If a person is identified by the machine as having hazardous material, what's the probability that they actually have hazardous material on them? Okay, so like I said, this one I'm going to set up as one of those tables like we were kind of doing with yesterday's stuff. So I'm going to make one of my things going one way like the hazardous stuff, and then the other way I'm going like if they were identified or not. So up top here, I'm going to do this as hazardous or not hazardous. So I'm just going to go H for hazardous, the other one not H for not being hazardous. And then my last group there, I'm just going to make totals. I guess I don't need to S there, total. And then I'm going to do the same thing going the other way, except for with the I. So I'm going to go I for they were identified as having the stuff or accurately identified. And then the other one would be not I, that they were not identified as having the material on them. Okay, so then this one's a little trickier because they don't actually give us just straight up information. We got to kind of combine some stuff together. So we've got information about the number of passengers there, and then we've also got those two percentages. So for the hazardous material, so 1 in 500 people actually had that hazardous material on them. So for hazardous, I'm going to put 1 here and 1 here because those people actually had hazardous material on them out of the 500 people. So what that would mean for the people that don't have it on them, out of the 500, there would be 499 that don't have any of that material on them. So on that group, I'm going to go 499 in both of those spots because those people didn't have that actual bad stuff on them. Now I'm going to do the same thing with my percentages, fill those into spots. So for the 98, so it says device accurately identifies 98% of people with the hazardous material that pass through. So the 98 is going to be the hazardous stuff. So the we're going to go 98 for the ones that are actually identified. And I'm going to do it as a decimal for my 98%. And then if 98% of people are identified, the people that would not be identified that do actually have this stuff on them would be 2%. So if 98% of people are identified, 2% are not identified, but they have that stuff on them. Okay, so that's why they're in that group. Now the next one here, so not hazardous materials, the other percent. So the other one accurately identifies 99% of people without hazardous material. So we're in the not hazardous material thing. Accurately identified is the ones that would not have it because they don't have it. So the accurate one is actually going to go down here this time for our 99% because they were accurately identified as not having it, so not for both. And then the opposite of that would be the 1%, and that would go there. So the people that were identified as having hazardous material on them, but they actually didn't have hazardous material on them. Okay, so then I just go through and figure out what actually those are equal to when we multiply them out, so we know those actual numbers in those spots. So like 1 times the 0.98 is just 0.98. The 1 times the 0.02, just 0.02 for that group. The 499 times 0.01 is 4.99. And then the 499 times 0.99 is 494.0. And I just got those numbers by multiplying. So now I'm going to make a totals category on the bottom as well. Okay, so then totals wise, these numbers we figured out here are actual numbers of people. So about 1 person is identified that actually has hazardous material, and about 5 people are identified that don't have hazardous material. So to get the total there, you would just take those two and add them together. So the 0.98 plus the 4.99, so 5.97, just adding those two together. And then I do the same with this 0.02 plus the 494.0. So not identified, the ones that actually have it is that small number there. The ones that aren't identified and don't have it is the big one there. So that's 494.03. And then what should happen with those two totals is it should always add to your total number of people, which was 500. So if you add those two together, it does give us 500, which logically makes sense because it's that many people and that many people. And then going across the other way, you can do the same thing. So like here, you'd add your 0.98 and your 0.02, so that would be 1. And then your not hazardous one, you do the 4.99 plus the 494.01, which is 499. And those numbers are going to be the same as our original one with the 1 in 500 people, because that was one person having hazardous material, 499 not having it, so that's why that works out that way. And then again, that totals to 500. So now what they're actually asking then from that information, it says if a person is identified by the machine as having hazardous material, so hazardous material is the stuff here, what is the probability that they actually have these kind of materials on them? So that's using this one here. But what we're going to want to do is we're going to want to do one of those conditional probabilities like we had before. So you're going to go the probability of the H, and then the line, and then the I. So if they're identified, what's the chance that they actually have it on them is basically what we're trying to figure out. So when we do this out again, it's always the intersection of the two groups divided by the probability of whatever the last letter is. So that I there. Then we just look at our things here and we try to figure these out. So like here, the intersection of the two groups would be capital H, capital I. That would be this decimal number here of the 0.98. So that would be our top number. And then our bottom number there is all of the people who were identified. So all of the people identified is all the stuff in this column here. So that's that 597 number. And then you would just take and you would divide those out just like we were doing before. And it comes out as a decimal. It's like 0.1642 when I did it out earlier, which would be about 16.42%. That one's a little trickier, trying to figure out what all goes in the table and that kind of thing. But as long as you can kind of get the table or the tree diagram set up, the probability part's actually not too bad, but the setup can kind of be a little bit of a pain. But that's it for notes. So you got this book page here. So 398, 1 to 11. Skip number 10 though, and then 11E seemed like a long one to write out, so I'll just skip that one too.